Hey guys, this is just a recording of the solutions for assignment 4 in Math 3274. Okay, so let's start with question 1. It says, prove by induction. Well, if you proved it another way, that's okay too. So I'll just say, prove for all mn and k. If m is less than n, then m plus k is less than n plus k. Okay. And some clues that induction might work. Well, if k equals 0, that would be the base case. Oh yeah, I guess we discussed in the class that a hint might be like just do induction on k. And some clues that might work would be that if k equals 0, it's trivial. That's kind of a good sign, or at least it's easier than just in general. And also, we're using addition, and addition is defined inductively, so that's a good sign too. Okay. So, P of k is going to be the statement that m is less than n implies m plus k is less than n plus k. And I guess we should include quantifiers for m and n, so let's say for all mn in the natural numbers. That's P of k. So, we have our base case is k equals 0. And the definition of m plus 0 is just m. And the definition of n plus 0 is just n. Okay, that's true for all m and n, since n plus 0 equals m by definition. Okay. Now, induction hypothesis. Right. Let's see, let's just assume for some k that if m is less than n, then n plus k is less than n plus k. Okay, and our induction step. Right, what should we do? Well, we suppose m is less than n, and now we have to look at m plus k plus 1 and compare that to n plus k plus 1. Okay. So the induction hypothesis implies that n plus k is less than n plus k. Okay. And what we want is that we want a k plus 1 instead of k. Right. So we have to know that we have to hope that we can add 1 to both sides of this inequality. If we can, then that would be good. Okay, so one way to do that is to remember from class if I'll use different letters, but if A is less than B, then A plus 1 is less than or equal to B. And also, you also have the inequality like C is less than C plus 1. Okay, so now, starting from here, we know that n plus k plus 1 is less than or equal to n plus k. And n plus k is strictly less than n plus k plus 1. Okay. Therefore, m plus k plus 1 is strictly less than n plus k plus 1. Okay. But the definition of the definition of m plus k plus 1 is you just add 1 to m plus k. In other words, m plus k plus 1 is this. M plus k plus 1 is just n plus k plus 1. In other words, we've shown that m plus k plus 1 is less than n plus k plus 1, which is the induction step. So we've shown that if m is less than n, then m plus k plus 1 is less than n plus k plus 1, so which is p of k plus 1. And then our conclusion, okay, by induction, p of k holds for all k. Which is the statement in this statement. I guess it doesn't hurt to rewrite that. So if m is less than n, then m plus k is less than n plus k. UD. Okay. Our next question, we have to starting from two natural numbers m less than n, we have to construct n minus m. That is the second problem. Let me write down the second problem. You have to show for all natural numbers m and n, if m is less than n, then m plus k is equal to n for some k. Okay, so the solution. Oh yeah, and I said that for some unique k, so I guess I'll just add that in. A is unique. So, we have to do a couple things. We should do this by induction. Let's try and do it by induction on n. So P of n is going to be the statement, if m is less than n, then there exists unique k, k with m plus k equals n. Okay, and our base case is n equals 0, which is trivial. There's no natural numbers less than 0, so there's nothing to show when n equals 0. Okay, trivial or vacuous. Okay. Now assume that n is a natural number, and if m is less than n, then there exists unique k with m plus k equals n. Okay. And now this is the induction hypothesis. Okay. And now we do the induction step. Okay. Suppose m is less than n plus 1. So there's two cases. When m is less than n plus 1, I mean, you can go back to the definition of less than to see this, but we know that m is either equal to n or m is less than n. Okay, so let's do the case that m is less than n. Okay, in this case, what happens? Well then, by the induction hypothesis, there exists unique k such that m plus k equals n. Okay, now let's add 1 to both sides. So m plus, I mean, I guess we should do it carefully. If we add 1 to both sides, we get m plus k plus 1 equals n plus 1. But this is the definition of m plus k plus 1. That's just n plus 1. Okay. Now there's the question of whether or not this is unique. Okay, and that suggests the following question, which I'll put in a box here. Essentially, if n, I'll use different letters, if a plus 1 equals b plus 1, then a equals b. Okay, that is actually something we kind of need to take care of. Okay, if we are able to show this, then since k is unique, this integer here, like this, the solution to m plus question mark equals n plus 1 will be unique. Okay. Because there's only one, because we know that there's only one k for this, and there's only one integer of the form k plus 1. Okay. So let's leave this till later, because we still, so assuming we have this, then this k plus 1 exists and is unique. So the other case is m equals n. Well then, m plus 1 equals n plus 1. This is k. Okay, so in this case, so we've shown p of n plus 1, and in this case we've shown p of n plus 1. Again, in both cases to prove uniqueness, we need this. So we are done. Okay, so if we can show this, well, let's just show this. Okay, let's try that. Let's show that if a plus 1 equals b plus 1, then a equals b. Okay, proof. What is a plus 1? It's just a union. What is b plus 1? It's just b union b. Okay. I mean, I'm sure there's many different ways to show this, but you know, these two sets are equal, and a is an element of a plus 1, so a must be an element of b plus 1. So a is in b union b. Either a equals b, you're done. So it must be, so the other case is that a is in b. Okay, what happens then? A is an element of b. Well, we can do the same thing. We can look at b is an element of b plus 1. Let's just see what happens. Let's look for b is in b plus 1. B plus 1 equals a plus 1. Okay. A plus 1 is just consists of a union the singleton of a. So either b is in a or b equals a. Okay. If b equals a, again, we're done. So we are done. So now we are in the situation where a is in b and b is in a. Okay. We write this in terms of less than. This is actually gives us like a contradiction in several different ways. You know, by transitivity, we now see that a is less than a, which is impossible, a contradiction, which we proved in class. Okay, and that concludes that the fact that if a plus 1 equals b plus 1, then a equals b. Okay. That tells us that this like the uniqueness of this k tells us the uniqueness of this k plus 1. When I think about it, there's probably a, you know, like a slicker way to do this, but oh well. Okay. So thank you for watching. If you have any questions, please send me an email. Okay.